In this video, we're going to analyze the electronic absorption spectrum of this cobalt-tris oxalate species using a Tanabe-Sugano diagram. This is a cobalt 3+ ion, so it's a cobalt 3d6 species. There's going to be a number of things that are going to make this a little bit more complicated than analyzing that nickel 2+ 3d8 species that we analyzed in the previous video. One just has to do with the fact that for a 3d6 ion, so here are the 3d orbitals with the 6 electrons occupying those 3d orbitals. We have 210 microstates possible. There is a quintet D term that represents the ground state electronic configuration. In addition, there's a series of triplet terms, a triplet H, a triplet G, 2 triplet F terms, a triplet D term, and 2 triplet P terms. In addition to the quintet and the triplet states, there's also a number of singlet states. A singlet I, 2 singlet Gs, a singlet F, 2 singlet Ds, and 2 singlet S terms. Of course, going from the high symmetry free ion, these are going to further split into lower degeneracy terms when we move into OH symmetry. Displayed in the lower left-hand corner is the D6 Tanabe-Sugano diagram. There are a number of different states in this Tanabe-Sugano diagram. There are quintet states, there are triplet states, and there are singlet states. In addition to the number of states that are possible with a D6 ion, we also have a further complication, and that's the fact that this species can be either in a high spin or a low spin state in an octahedral coordination environment. In its high spin state, you have a small value for delta O, or 10 dq, and because of this, you'll have 4 electrons occupying the T2G orbitals, and you'll have 2 electrons occupying the EG orbitals. Therefore, you'll have ground state quintets. Increasing delta O will change the spin state. So, when delta O becomes large relative to the pairing energy, all of the electrons will occupy T2G orbitals, leaving an empty EG set. So all 6 electrons will be in those T2G orbitals, and this will result in a singlet ground state. This is reflected in the Tanabe-Sugano diagram. If you look down at the 10 dq equating to approximately 19.5, you'll notice that there's a discontinuity. At small values of 10 dq over B, you have a high spin species, which is represented by a quintet ground state originating from that quintet D term. As you increase in 10 dq over B, eventually that no longer becomes the ground state term and rises in energy relative to the new ground state term. As we cross over, we're now a low spin species, and the ground state term originates from that singlet I free ion value. So now we have a singlet ground state. So when dealing with this, we have to determine whether or not we're dealing with a low spin or a high spin complex. And this will be reflected in the electronic absorption spectrum, as we'll see as we go through and analyze this. Now, if you look at this Tanabe-Sugano diagram, you're going to notice a few things that are going to simplify the analysis. The first is that for a high spin species, there's only one spin allowed transition, the transition from a ground state quintet into an excited state quintet. On the low spin side, there's a large number of spin allowed singlet transitions. However, if you look at the scale of your E over B, you'll notice that this is a huge scale and that most of these transitions occur in the vacuum UV region of the electronic absorption spectrum. Therefore, a lot of these transitions are not going to be observable when we go through and analyze a UV vis spectrum. So we'll be focusing in on just one region of this Tanabe-Sugano diagram, which will further simplify the analysis. I've gone through and expanded the D6 Tanabe-Sugano diagram so that we can focus in on the low energy transitions. So going through, the first thing we have to decide is which side of the Tanabe-Sugano diagram do we want to start working with, the high spin side or the low spin side. So we know that this is a cobalt 3+ species, and we know that cobalt 3 is typically low spin. So this means that we're going to have a large value for 10dq. So we're working over here on the right-hand side of the Tanabe-Sugano diagram when we're transitioning to the low spin species. So we're going to be looking at transitions originating from this singlet A1G ground state term. We can estimate where we want to start by knowing a little bit about the chemistry of cobalt 3. So for example, a good value for 10dq for cobalt 3 with weak field ligands would be approximately 20,000 wave numbers. Furthermore, we can estimate this value for B. For a low spin octahedral compound, a good approximate value for B is approximately 600 wave numbers. So we can work starting with a 10dq over B value of approximately 33 as our initial guess. So our initial guess is going to originate from this point right over here, and we're going to be looking at these transitions from that singlet A1G up into the singlet T1G and the singlet A1G further up into the singlet T2G state. Approaching this like we did for the nickel 2 plus 3D8 species, the first thing we're going to do is get the ratio of nu2 over nu1, which is 23,529 wave numbers over 16,611 wave numbers, which equals 1.416. So we're going to be looking for a ratio of our E over B's that equal 1.416. At a 10dq over B equal to 33, we can go through and do that vertical excitation. So drawing that straight line up and then working across and extracting our E2 over B and dividing that by the E1 over B. So when we do this, this equals 43.7 over 30.4, which equals 1.44, which is a bit on the high end. We need to lower that ratio, which means we're going to move towards the right in 10dq over B values. So going through and moving to the right to a value of 34.5. We can draw that vertical line and then do our horizontal crossings. Going across, getting our E2 and our E1 over B values, and that's going to equal 44.8 over 31.5, which equals 1.42, which is a good value. It matches the value that we calculated for the ratio of the energy of the transitions fairly well. So we're going to go with a 10 dq over B value of 34.5. Now we're going to go through and calculate B and the value for 10 dq or delta O. So that E2 over B value is equal to the energy of that transition, 23,529 wave numbers, over the value that we calculate, over the value for B, which is equal to 44.8. So solving for B, we get a value for B equal to 525 wave numbers. E1 over B is equal to 16,611 wave numbers divided by B, which was equal to 30.4. So B is equal to 546 wave numbers. What we're going to do is we're going to average these two together to get the average value for B. So the value for B that we're going to report is 535 wave numbers. Going through, we're going to now calculate the value for 10 dq. So 10 dq over B is equal to 10 dq over 535 wave numbers, which is equal to 34.5. So solving, we get a value for 10 dq equaling 18,500 wave numbers. We can go through and calculate the value for beta. So that's just the value of B that we calculated for the complex over the free ion, which is 535 wave numbers. The value of B for a free cobalt-3 ion is 1,065 wave numbers. So this equals 0.502. So the electron cloud is fairly largely expanded relative to the free ion, reflected in this small value that we calculate for beta. So there's a lot less electron-electron repulsion in this complex relative to the free ion. And this is the reason that we can have this low spin state for this cobalt-3 complex with a relatively small value for 10 dq or delta O equal to 18,500 wave numbers. The reason for this is that this beta value reflects relatively small electron-electron repulsion energies, allowing this low spin state to occur for this cobalt-3 plus ion despite this relatively small value for delta O for a low spin complex. Now that we've tackled how to handle an octahedral compound where you can have a high spin or a low spin state using a Tanabe-Sugano diagram, in the next video we're going to tackle how to calculate delta T, the splitting in the E and the T2 energy levels in a tetrahedral complex using Tanabe-Sugano diagrams.